On Monday, we looked at group 1. That is, we've started with the S block elements. But today, and we're able to finish the S block, the group 1 element. So today we start with the group 2 elements. And I hope you have checked the elements because I've already uploaded both the slide and the recorded video. So today we look at group 2 elements. For our group 2 element, please mute yourself so that you don't disturb my lecture. So for group 2 element, we have our beryllium, magnesium, calcium, strontium, barium, and radium. Among the group 2 elements, your radium is radioactive. Among your group 1 element, your francium is radioactive. So please note this. And for electronic configuration, who is raising his or her hand? Is that Izuchukwu? Is somebody raising his or her hands?
Sorry, it was a mistake. I'm sorry.
Okay, thank you. Okay. So we have, for the electronic config, of course, we know the symbol. We have to note the symbol. Then the electronic configuration. We have our beryllium, beryllium, magnesium, calcium, strontium, barium, and radium. Just like our group 1 element, they have 1 electron in their valence orbital. For the group 2 element, they have 2 electrons in their valence shell. And we also notice that as we go down the group, these shells actually increase. That is why we have 2s, 3s, 4s, 5s, 6s, 7s. So the size of the element is actually increasing. Despite increasing the size, each of them still have 2 electrons in their valence shell. So that is why they are referred to as group 2 elements. For ionization energy decreases down the group, just like the group 1 element, because of course the increase in size, there's increase in atomic radius, there's a decrease in nuclear pool or nuclear charge, and also there's an increase in shielding effect. So that is why ionization increases down the group. Melting and boiling point also reduces. Beryllium has the highest melting point, just like in group 1, lithium had the highest melting and boiling point because of the nuclear pool, which is very strong. So the elements of your lithium and beryllium are very close to the nucleus. They are tightly held. That is why their melting and boiling point increases. Why, as we go down the group, the melting and boiling point reduces. Of course, ionic radius increases. Now, somebody asked a question. There was somebody that asked the question during our last lecture towards the end. Why was it the melting? Yes, the melting point. I can remember that question very well. The melting point for your group 1 element, you see that there was a general trend, they reduced down the group. But for group 2, we can see magnesium is 650, calcium is now higher. We expect it to be reducing down the group. And I rightly answered that question that it's because of the way each element is the structure. So the melting points do not vary regularly, just like the group 1, mainly because the metals adopt different crystal structures. So it will depend on the crystal structure of the element that will determine the melting point. If the crystal structures are well packed, of course, we expect a high melting point. But if the structures are not well packed together, then we expect a lower melting and boiling point. I think that was the question that particular guy asked, and I think this answers it better. Sorry, I don't know why it's hanging. Okay. So your group 2 element, they are all metals, and they are known as alkaline earth metals. Your group 1 are known as alkaline metals. Why these are known as alkaline earth metals? Just like the group 1 element, they are also good reducing agents because they are metals. And their compounds, because the difference in electronegativity when they react with non-metals is high, so they usually give ionic compounds. And for their oxides and their hydroxides are basic. Of course, the elements they are basic, so their hydroxide and oxides are also basic. And they liberate hydrogen when they react with acids. Now, like lithium in group 1, I told you that for each group element, the first element usually behave differently from the other element. We saw this in lithium, and we're also going to see this in beryllium. Because, can you mute yourself, please? Who is Favor? Favor, Favor. I will remove you from this class. Duro Waye Favor. I will remove you from this class. Duro Waye Favor. I will remove you from this class. If you keep on disturbing my class, mute yourself. So just as I said, the first elements, because of their small size and their high charge, they usually behave differently from the other elements. We saw this in lithium, and we're also seeing this in beryllium among the group 2 elements. You also see this when you get to group 4, you see it in carbon. So most of the first elements, because of their small size and high charge, they usually behave differently from elements in their group. So we say a reason for the electrons are not well shielded from its nucleus. So they're very close to the nucleus. So their size is usually very small and they have a high charge. So we say due to small ionic radius or small size, by the time I remove that favor from here, I think we have a better lecture. Let me remove him or her. Where is the person self? So we can now have some quietness in this. I've put him or her in the waiting room. So let her or her, let me catch you. I will just remove you from my lecture. You can't be disturbing the whole class. So as I said, the reason, because of the small ionic radius, representing very dense center of positive charge and high polarizing power. I think the last lecture I took time to explain what the polarizing power is when we talked about lithium. So because of the small size, they have a very high charge. And when they have a high charge, what it means is that they can attract electrons. And when they attract electrons, have high polarizing power. And for your beryllium, the compounds are also more covalent than ionic, just like we saw in lithium. For your beryllium is amphoteric. The oxide is also amphoteric. Your beryllium is not basic like the other elements. Your beryllium is amphoteric, and the oxide is also amphoteric, and it is not basic. I don't know why it's just hanging. And because of its small size and high charge, it forms complexes more readily than other members of the group. Just like your lithium among the group 1 element is the only element that forms a complex. Likewise, your beryllium, because of the small size and high charge, it can form a complex. It dissolves in alkaline, unlike other metals in the group. The other metals are alkaline, they are basic. Your beryllium is amphoteric, so it will dissolve in alkaline and base, but it will not dissolve in water. So that is what characteristics of amphoteric elements or compounds. So your beryllium will dissolve in alkaline, and it also dissolve in acid because it's amphoteric. So like group 1 metals, group 2 metals are also very reactive and are prepared by electrolysis. Because we say they are very reactive, so they don't occur in their free state. They don't occur in their free state. And because they don't occur in their free state, for us to get them in the pure form, then we have to prepare them by electrolysis. But as I said, we're not going to go into deep into electrolysis. So let's look at their compounds. Just like your group 1, they form oxides. They form oxide, that is, they burn in air. They burn in air or they react with oxygen to form oxide. They also form the normal oxide, and as we go down the group, we form more of the peroxide. So group 2 metals form peroxide down the group, just like your group 1 metals. Beryllium, in terms of reactivity, is unreactive because your beryllium has a thin film covering, just like aluminium or your aluminium oxide. So that is how your beryllium is. So your beryllium is very, very unreactive, but it can react above 600 degrees Celsius. And this has to be in the powdered form. Of course, we know that as we increase the surface area, reactivity increases. So if you get it in the powdered form, then it can be more reactive. But generally, your beryllium is unreactive, so it does not react with oxygen. But your beryllium oxide is formed with ease and increased stability. So as we go down the group, your barium peroxide is formed. That's what I was trying to explain, that as we go down the group, we form more of peroxides. The higher ones form normal oxides, while the lower ones form peroxide and then superoxide. But your barium forms your barium peroxide. Now we look at the oxides and the hydroxides. The oxides and hydroxides of your group 2 element. Of course, with the exception of your beryllium oxide, which is insoluble in water. I told you because your beryllium oxide is amphoteric, we don't expect it to be soluble in water. It will only be soluble in acids and their base. So your group 2 oxide, which we already know is formed by a reaction of the metal with oxygen to form the oxide. Now, the oxide can actually react with water to form hydroxide, which is an alkaline solution. But for magnesium hydroxide, your magnesium or your magnesium oxide does not react with water. It reacts more with steam. Your magnesium can react with steam to form the oxide. But formation of your magnesium hydroxide is usually by a reaction of your magnesium chloride and sodium hydroxide. Please note this. Formation of your magnesium hydroxide is not by a reaction of your magnesium oxide with water. Your magnesium will react with steam to form your magnesium oxide. But your magnesium oxide does not react with water to form your magnesium hydroxide. It actually reacts with your magnesium chloride react with sodium hydroxide to form your magnesium hydroxide. But
Can you come again? I'm a bit confused.
Your group 2 oxide can react with water. to form the hydroxide. Your group 2 metal can react with oxygen to form the oxide, which is what we have done here. The oxide form can react with water to form hydroxide. But for your magnesium will react with steam, not water, to form your magnesium oxide. It does not form magnesium hydroxide. For you to form your magnesium hydroxide, you have to react your magnesium chloride with sodium hydroxide. Your magnesium oxide is not reactive with water. Just like your beryllium oxide, there's some thin covering that makes it unreactive. So it will react more with steam and not with water. So for you to form your magnesium hydroxide, you have to react your magnesium chloride with sodium hydroxide. But the other group 2 element, their oxide can react with water to form your magnesium hydroxide. And again, the hydroxides are usually basic, strong alkaline solutions, but your magnesium hydroxide is weakly basic. So that is why it's used as an antacid in indigestion tablet. That is your milk of magnesia. Your mismag, that is your magnesium hydroxide, because it is weakly basic. So in preparing the hydroxide, the oxide, the nature of the oxide or the nature of the hydroxide or the nature of the solution will determine the use of these elements. So your magnesium hydroxide, because it's weakly basic, of course, as we go down the group, we expect basicity increases. But of course, basicity increases because that is why your calcium hydroxide is actually more basic than your magnesium hydroxide. So your magnesium hydroxide is weakly basic, and that is why it's used as an antacid. Your beryllium hydroxide is amphoteric, just like your beryllium oxide is amphoteric. Why the others are basic, but your magnesium hydroxide, as I told you, is weakly basic, and basicity increases down the group. Our calcium hydroxide and barium hydroxide are called your lime water and your baryta water, and you can use them to test for your CO2 gas in the laboratory. So in a situation where you don't have your calcium hydroxide, you can actually use your barium hydroxide to test for your CO2. And they are made by reaction of their oxides with water, unlike your magnesium, which is made by a reaction of your magnesium chloride and sodium hydroxide. Now we've looked at the oxides, how they are formed, reaction of the metal with oxygen to form the oxide. We've looked at the hydroxide, reaction of the oxide with water. Now we'll now look at their halides. Halide, that is, of course, we know its reaction with halogens. The halogens, which are the fluorine, the bromine, the iodine, the chlorine. But the most common halides is usually the chlorides. The chlorides are usually the most common halides. So reaction of the metal with the halogens will give you the halides. Example, you react the metal, let's say your calcium with chlorine, that will give you your calcium chloride. And the halides are soluble in water because they are ionic. So they are soluble in water. And they also easily form hydrates, that is having water of crystallization. They also form hydrates, having water of crystallization. So most times the compounds are usually hydrated, not usually anhydrous. For the anhydrous ones, they actually absorb water from the atmosphere. They're usually the liquescent. Now, still looking at your beryllium, which is different from the other element, your beryllium chloride has a linear structure. Your beryllium chloride has a linear structure. So your beryllium can exhibit two types. We have the linear structure and we have the polymeric structure. And of course, we already know our beryllium is covalent because as we go down the group, basicity increases, acidity reduces. So your beryllium is more covalent, is more acidic, and less basic. So your beryllium chloride exhibits covalent character. So your beryllium can be linear and it can be polymeric. Now, the ionic character in the chloride also increases down the group. The ionic character in the chloride increases down the group. And as I said, they usually form hydrated salts because the anhydrous salt are usually deliquescent. Deliquescent, that means you can use it as a drying agent. So most times the compounds you usually work with in the lab are usually dehydrated salt. The deliquescent, the anhydrous ones are usually deliquescent, like your calcium chloride, and it's used as a drying agent. Now we'll look at their carbonate and the hydrogen carbonate. We saw this even in our group 1 element where we looked at the oxo salts. I don't need to go through what oxo salts are again. So we should know by now that your carbonate and hydrogen carbonate are oxo salts of your group 2 elements. We talked about the carbonate of our group 1 element, that they are solids. Their hydrogen carbonates are also solids, except your lithium hydrogen carbonate, which is a solution for your group 1 element. So for your group 2 carbonate, are also solids. So unlike the carbonate and hydrogen carbonate of group 1, group 2 carbonate are slightly soluble in water. So invariably, your group 2 carbonate are less ionic. Your group 1 carbonate are more ionic. So the more ionic nature, the more soluble. The less ionic nature, the less soluble. So your group 2 carbonates are less soluble in water. So invariably, they are less ionic. And the solubility decreases down the group. Solubility of your group 2 carbonates decreases down the group. But for your group 2 hydrogen carbonate, they are all liquids. They are all in solution. Solution. Your group 2 hydrogen carbonates are all solutions. So that is why your lithium is behaving like your group 2 element. The group 1 carbonates are solid, but they are slightly soluble in water. So invariably, they are less ionic. But your hydrogen carbonate, the group 2 hydrogen carbonates are all solution. So on heating the carbonate, they actually decompose into oxide and CO2. And the ease of decomposition decreases down the group. So I've already explained your group, or like your group 1 metals, which possess solid hydrogen carbonate. The hydrogen carbonate of your group 2 metals only exists in solution. So your group 2 hydrogen carbonate exists in solution, just like your lithium hydrogen carbonate in group 1. Now we look at the sulfates. Your sulfate is also an oxo salt. So we've looked at the carbonate. Sulfate, that is your beryllium sulfate, magnesium sulfate, calcium sulfate, strontium sulfate, and your barium sulfate. Now, when we talk about this oxo salt, we are more interested in their solubility, their stability, because we normally use them in qualitative analysis. Solubility of sulfate in water decreases down the group. Solubility of sulfate in water decreases down the group. So why does that happen? Why? Because So what invariably, what it means that your beryllium and your magnesium will be, their sulfate will be more soluble in water than your calcium, strontium, and your barium. Why is this so? Solubility of your group 2 sulfate and even their carbonate decreases down the group. What happens is that as we go down the group, the size of the cation increases. And as the size of the cation increases, what happens is that when we're talking about solubility, we look at hydration energy. That is the amount of energy that will be released when the ions, or when the ions undergo hydration, when the bonds are broken. So that is what we mean by hydration energy. So as we go down the group, what happens is that size increases, size of the cation increases. So the hydration energy and the lattice energy, that is the energy required to dissociate 1 mole of an ionic compound. You need to break that ionic compound. Why the amount of energy released is actually the hydration energy. So hydration energy and lattice energy reduces. But due to the large size of the anion, that is your sulfate ion, your your carbonate ion, they are large. Because these ions are large, what happens is that hydration energy will decrease more than the lattice energy. So for any compound to be soluble, what it means is that the lattice energy must be more than the hydration energy. But when the hydration energy is low, then solubility reduces. So solubility trend is due to the high enthalpy of solvation of the smaller beryllium and magnesium ions, unlike the calcium, strontium, and the barium ions, which are larger. So that is why solubility of their sulfate will decrease down the group, because your beryllium and your magnesium ions, they have a high enthalpy of solvation. The ions are small size, high charge. So they have high enthalpy of solvation. Why these ones? Their enthalpy of solvation will be small. So that is why your beryllium sulfate and your magnesium sulfate will be soluble. Your calcium sulfate will be spirally soluble. Your strontium and your barium sulfate are insoluble. And we are going to see the importance of this solubility as we go down the lecture. So your sulfates of your beryllium, magnesium, and calcium are usually found as the hydrated crystals. And for the stability of your group 2 sulfate, stability will actually depend on basicity. The more basic, the more stable the sulfate. So your strontium sulfate will be more stable than your barium sulfate, because your barium sulfate is less ionic, while your calcium and strontium sulfate will be more ionic and more basic. So the more basic, the more ionic, and the more stable. Now, we look at some uses of your group 2 sulfate based on solubility. Sorry. Your magnesium sulfate, your hydrated magnesium sulfate, is used as a mild laxative. Note that your magnesium, your beryllium, and your magnesium have high enthalpy of solvation, so they are more soluble. And that is why we can see that our magnesium sulfate is our Epsom salt. So it's used as a mild laxative. So because it's soluble in water, then you can use it as a mild laxative. So their solubility has to do with their uses. Your calcium sulfate, known as gypsum, are also known as your plaster of Paris, are useful in treatment of bone. Let's look at the solubility of our calcium sulfate is spirally soluble, and that is why we see we are using it as plaster of Paris. So because it's spirally soluble, they can actually use it in making our POP or even for broken bones. So because it's spirally soluble, you can actually mold it to what you want before it sets. So that is why your calcium sulfate is used as plaster of Paris and in setting of using in treatment of bone. Your barium sulfate, let's look at our barium sulfate. Our barium sulfate is insoluble. So let's look at the use. Your barium sulfate is used in diagnosing stomach ulcers because it is insoluble in water and opaque to X-rays. So what happens is that it's used in the treatment of stomach ulcers to be able to take the X-ray of the stomach. What happens is that because it's insoluble, most times the patient is meant to ingest the barium sulfate because it will not dissolve in the human body, it's insoluble. So it provides a shadow of the stomach. And once it provides a shadow of the stomach, then the X-ray picture of the stomach can then be obtained. So solubility of the sulfate actually relates to the uses of these compounds. Now, let's look at some other uses of your group 2 element. Your beryllium is used in nuclear reactors. Magnesium in making alloys. Alloys, that is when you combine two metals. And it's useful for aircraft structures because your magnesium is light, because it's very light. For our calcium, it's useful in body for healthy bones. So most times when you have fragile bones, so most times they actually ask you to take a lot of calcium. So our calcium is useful for healthy bones. Your strontium is useful in radiochemistry. We've already talked about our barium, it's used as a barium meal in medicine, and I've already explained that your barium sulfate. Any question?
Sorry, ma.
Okay.
In the beginning, you were explaining why the melting point decreases, then increases. I didn't really get you.
Yeah. Okay. You know, I said somebody asked this question on Monday, why for your group 1 element, you see that the melting point decreases down the group. But for your group 2 element, you see that the melting point decreases down the group quite well. But when we look at magnesium and calcium, we see that there's an exception. We expect your magnesium to be higher than your calcium, but here your calcium is higher than your magnesium. We are saying that this difference in melting and boiling point for your group 2 element is because of the kind of different crystal structures. If their crystal structures are well packed, just like your calcium, then we expect the melting and boiling point to be higher. But for your magnesium, the crystal structures are not, it's irregular, it's not well packed. So because of that, you have your magnesium is exhibiting a lower melting point compared to your calcium, because we expect it to follow a particular trend. But when it got to magnesium and calcium, that trend is no longer there. So we see that the melting point do not vary regularly, unlike your group 1 element, because the metals adopt different crystal structures. If the structures are well packed, tightly packed, well packed together, then we expect a high melting point, because you need to break those crystals because they are well packed. But if they are zigzag, they are not well packed, of course, so breaking them will not be very difficult. So that is what I was trying to explain here compared to group 1 elements.
Thank you.
Okay. Any other question?
No, please, I didn't get it.
Sorry, ma, are the slides available?
I will put them immediately after the lecture. I'll put them on the lecture, the recorded lecture on the LMS. The other ones have been on the LMS.
What about the
What about the what?
boiling?
It's the same. because of the way these crystal structures are. That is actually what affect the melting point and boiling point. Unlike the group 1, where they have a particular trend, they are just reducing down the group. But because your group 2 elements, the way the crystal structures are packed, that is actually what affects the melting and boiling point.
Yes. I didn't get the part of where you said how lattice energy and hydration energy affects solubility of the compounds.
Okay. What I'm saying is that when we talk about lattice energy, you are actually looking at the energy you need to dissociate the ionic molecule. That is to break that ionic molecule. Now, hydration energy is the amount of energy released when the ions undergo hydration. That is when they dissolve in water. What is the energy that is given off? So lattice energy and hydration energy will relate to solubility. So what I said is that the solubility of we are looking at that solubility of your carbonate and your sulfate reduces down the group. Why is that so? That down the group, what happens is that size of the cation increases. Of course, we are going from beryllium to magnesium to calcium to strontium to barium. So the size of the cations are actually increasing. Of course, each of them is a cation. So the size of the cation increases. So as the size of the cation increases, the hydration energy and the lattice energy reduces too. But due to the large size of the anion now, because we are looking at the oxosol, the carbonate and the sulfate, the anion, let's look at your barium. Your barium 2+ is your anion. Your SO4 2- is your barium 2+ is the cation, while your SO4 2- is the anion. So what happens is that the size of the anion increases. And as the size of the anion increases, what happens is that your hydration energy decreases more than the lattice energy. So once the hydration energy is low, because hydration energy has to do with the energy that you release when these compounds dissolve in water. So if the hydration energy is reduced, of course we expect solubility to reduce. If hydration energy is high, then we expect high solubility. If hydration energy is low, then we expect low solubility. So because the size of the anion is, did you not get it?
So for a compound to be soluble,
yes,
the hydration energy has to be greater than the lattice energy.
Good. Yes. Because the hydration energy is the amount of energy released when the ions.
Thank you.
You got it?
Yes, ma. Thank you.
Okay. So you have hydration. You have lattice has to do with, when you have an ionic compound, the bond is the lattice energy that you have to break. But now for hydration is the amount of energy released when they now form that solution. When they are hydrated, they are now in solution form. So once the hydration energy is high, then we expect high solubility. But once the hydration energy is low, then of course, low hydration energy leads to low solubility. So any other? I'm still taking questions.
Ma, is hydrogen carbonate and bicarbonate are they the same thing?
Hydrogen carbonate and yes, is that you call it hydrogen carbonate or you call it a bicarbonate?
Okay, thank you, ma.
Okay.
Sorry, ma.
Okay.
I did not understand that barium meal.
You want to take the barium meal?
No, ma.
Huh?
No, ma. I didn't get the explanation.
Okay, listen. Okay, sorry. Let me tell you. Barium meal. Barium forms alloys with other metals such as lead and calcium. Its sulfate is used as barium meal in medicine. This is where I explain the barium meal. That is your barium sulfate. I told you it's used in diagnosing stomach ulcers. Because your barium sulfate, we have looked at the solubility of the sulfate. Your barium, your strontium and your barium sulfate are insoluble. So because they are insoluble, it can be used as a barium meal where the patient is made to ingest the barium sulfate, ingest it into the body. Because it's insoluble, so it will just be there, it will not dissolve, it will not affect. It will only go to the stomach and cast a shadow of the stomach. So when it casts a shadow on the stomach, then you'll be able to take the X-ray of the stomach to actually know where the ulcer is. So that is actually what we mean by barium meal. It's actually the barium sulfate that is used in diagnosing stomach ulcers.
Thank
Are
you,
we good? Okay. Any other question?
Ma.
Mm-hmm.
There's this slide on S law and entropy. It is not on L.
Who taught you? The group before me?
Yes.
Okay, I will let them know. What did you what slide is that?
S law and entropy, thermodynamics.
S law?
Entropy.
Okay. Okay, I'll let them know.
Thank you, ma.
Okay. So, in the absence of any other questions, so we'll meet on Friday by 8 o'clock. Okay, so we'll meet on Friday by 8 o'clock. So I'll put the recorded slide and the slide itself on the LMS. So see you on Friday by 8 o'clock.
Thank you, ma.
Okay,
Okay,
bye.
thank you, ma. Bye, ma.
Thank you, ma.
Bye.
Thank you, ma. Thank you, ma.
Thank you, ma.
Thank you, ma.